Every structural change in Postgres triggers an access-exclusive lock, which immediately blocks all incoming read and write operations on the target table until the current transaction finishes. This behavior often leads to unexpected application downtime during routine deployments. When a migration waits for a lock, it sits in a queue. Every request arriving after the migration command must also wait, even if those requests only need simple read access. This creates a massive backlog that can crash your connection pool.
To prevent a migration from bringing down the entire system, set a lock timeout for the session. This command instructs Postgres to abort the migration attempt if it cannot acquire the necessary lock within a specific time window, like 500 milliseconds. Always configure these settings within the specific database session used for migrations. Applying a short lock timeout globally would break normal application queries, so keep these parameters restricted to your migration scripts or deployment tool configuration. Encapsulate the timeout setting and the structural change within a single transaction block. This ensures the timeout is reset automatically if the connection returns to a pool, preventing leaked settings from affecting subsequent unrelated database operations.
Since migrations might fail due to lock timeouts during peak traffic, implement a retry loop in your deployment script. Use an exponential backoff strategy to wait longer between each attempt, increasing the chance of catching a quiet window in table activity. In Postgres version 11 and later, adding a column with a constant default value no longer requires a full table rewrite. The database now stores the default value in the system catalog, making the operation nearly instantaneous regardless of table size.
Adding a column as not null with a default is safe in modern Postgres, but adding a not null constraint to an existing column requires a full table scan. This scan holds an exclusive lock that blocks all concurrent operations. Standard index creation blocks writes until the index is built. Use the concurrently keyword to allow the database to build the index in the background while still permitting other sessions to insert, update, and delete data in the target table. Concurrent indexing performs two table scans. The first scan builds the initial index structure, while the second scan captures changes that occurred during the first pass. This ensures full data consistency without requiring a long-duration write lock.
Monitor the progress of background index builds using the system view named Postgres Stat Progress Create Index. This view provides real-time statistics on the number of blocks processed and the current phase of the concurrent indexing operation. If a concurrent index build fails, it leaves behind an invalid index entry that still consumes disk space and slows down catalog lookups. You must manually drop the invalid index before attempting the concurrent build again. When adding a check constraint or a foreign key, use the Not Valid clause. This tells Postgres to enforce the rule for new data immediately, but skips the time-consuming scan of existing rows that would otherwise require a heavy lock.
After adding a constraint as not valid, run the validate constraint command. This process performs the necessary table scan to verify old data, but only acquires a share update exclusive lock, which does not block reads or writes. Postgres cannot add a unique constraint concurrently in one step. First, create a unique index using the concurrently keyword. Once the index is valid, add the unique constraint by referencing that existing index, which avoids a secondary table scan. Implement foreign keys in two distinct phases to maintain availability. First, add the constraint with the not valid flag. In the second phase, validate the constraint. This split prevents long-duration locks on both the child and parent tables.
Directly renaming a column requires a lock and immediate application code changes. Instead, create a view that aliases the old name to the new name. This allows the database and the application to transition names at different times without downtime. When changing a column format, create a new shadow column alongside the original. Use a trigger to replicate every write from the old column to the new one. This keeps both columns synchronized while you migrate existing data in the background.
The synchronization trigger must handle inserts and updates. It should take the value from the old column and apply any necessary transformations before saving it to the new column, ensuring the new format is populated for every new write operation. Migrate existing rows to the new column using small batches. Updating millions of rows in a single transaction will bloat the table and lock it for a long period. Process 10,000 rows at a time and include a brief sleep period. Frequent updates during migrations create dead tuples. Monitor the dead tuple count and the auto vacuum progress.
If the vacuum cannot keep up with your migration batches, the table will grow significantly, leading to degraded read performance across the system. Before switching the application to the new column, verify that all rows are synchronized. Run a count query to find any rows where the shadow column is null or does not match the transformed value of the original column. Once synchronization is complete, update your application code to read from and write to the new column. Since the trigger is still active, any writes to the old column during the deployment window will still reach the new column safely.
After the application successfully uses the new column, the synchronization trigger becomes obsolete. Drop the trigger and its associated function to reduce the overhead on every write operation and to simplify the database schema for future maintenance. The final step is dropping the original column. This requires an access-exclusive lock, so apply the lock timeout strategy again. Ensure no legacy reports or secondary systems are still querying the old column name before you execute the drop. Changing a column from integer to big int is a common requirement as tables grow. You cannot alter the type directly without a full table rewrite. Use the shadow column and trigger method to perform this transition with zero downtime. Adding a value to an existing enum type can be done outside of a transaction block in Postgres. This allows the change to be visible immediately without holding locks on all tables that use that specific enum type. Use the Postgres locks system view to identify which transactions are holding or waiting for locks. Join this view with Postgres stat activity to see the actual structured query language text causing the blockage and the specific process identifiers involved. When your migration is stuck, look for the process identifier that has granted status on the same table but is in the state idle in transaction. These sessions are the most common cause of migration timeouts and application queuing. If a non-essential background task is blocking a critical migration, use the function pg_terminate_backend. This kills the connection and releases its locks, allowing your migration to proceed. Use this tool with caution to avoid interrupting user transactions. Deadlocks occur when two transactions wait for locks held by each other. To minimize this during migrations, always acquire locks in a consistent order across your application and scripts, and keep the duration of your transactions as short as possible. Postgres supports transactional data definition language, meaning you can roll back schema changes. However, concurrent index creation and certain enum additions cannot run inside a transaction block. Plan your script boundaries to accommodate these specific database engine requirements.
Any transaction, even a simple read, prevents the database from vacuuming dead tuples across the entire system. Long-running transactions during migrations can lead to massive table bloat and performance degradation, so commit your changes frequently. For massive data transformations, it is sometimes faster to create a new table, populate it, and then swap names. This requires a brief period of downtime or a complex trigger setup, but it ensures the resulting table is perfectly optimized and compact. Integrate migration checks into your continuous integration and continuous delivery pipeline. Use automated tools to detect commands like alter table or create index that lack the necessary safety keywords or timeouts before they ever reach your production environment.
Before running a migration, use a script to estimate the time required for any necessary scans. Analyzing table sizes and existing index definitions helps you predict if a migration will fit within your defined lock timeout windows. Never change a schema in a way that breaks the current version of your application code. Deploy the database changes first in a backward-compatible manner, then update the application code, and finally remove any temporary database shims or legacy columns. Non-blocking migrations require more planning and multiple deployment steps, but they are essential for maintaining high availability. By mastering lock timeouts, concurrent indexing, and staged constraints, you ensure that your database evolves without ever interrupting your users.